Hello dear students, and welcome to this substructure component of structure 2. This is topic 2, and in this video we'll learn how an engineer classifies a soil, basically engineering classification of a soil. Now all the soil we see around us, they can be either one of two categories. The first one, we call it cohesive soil, basically soils with clay in it. Some other words we use for this type of soil, we also call it fine-grained soil, and sometimes reactive soil, especially when these type of soil shows expansion and contraction behavior with moisture change. We'll see about those things a bit later anyway. The second type of soil we see around us, we call it non-cohesive soil or cohesionless soil, basically sand with low or no percentage of clay in it. Now it can also be a gravelly soil with some percentage of clay in it. Now before moving into deeper areas of soil classification, let's have a quick look how we classify a soil particle itself. Soil particles, they're classified depending on their particle size, basically. So if we have a soil particle that is within the size between 75 and 4.75 millimeter, we call it a gravel. And it's a sand particle if the size ranges between 4.75 to 0.075, and anything smaller than that, that is 0.075 millimeter or smaller than that, we call it fines. It can be either a silt or a clay. Now that's one organization classifying the soil like that, and there are many other organizations, they have their own standards. So it can be a bit confusing to start with. Now, we'll get to this in a second. Now, once I know how much of what size particle a soil has, I can tell a soil by its name. That is basically, we can use a chart like this. This is very common. This is a chart commonly used by agricultural engineers. What they will do is, if they know the percentage of silt, percentage of clay, and percentage of sand, they can draw some lines like this, say for sand percentage 50, 40% clay, and 10% of silt. The classification of that soil will be sandy clay. Anyway, we engineers, we usually do not rely on this type of classification. What we rather use is what we call Unified Soil Classification System. This system is used all over the world, and the soil is named using a two-letter abbreviation. The classification is based on soil's particle size and its distribution, especially for gravelly, sandy types of soil. And then other type of soil, their behavior is often controlled by the plasticity of the finer particle. We'll learn about what is plasticity a bit later anyway. So this plasticity we'll be often using to classify clay or silt type soil. For gravel and sandy type soil, we use particle size distribution. And because its behavior is affected by its particle size, its particle shape, and its distribution. And if we have a clay or silty type soil, its behavior is often dominated by its chemistry, its affinity towards water. That is another word for plasticity. So we'll look at that a bit later. Now, let's have a look at the particle size and what we call them according to Unified Soil Classification System. So in this chart, you can see the grain size are the numbers in here, and what we call them are presented in here. So a gravel in according to UCS or USC or Unified Soil Classification System, we'll call a soil particle a gravel if its diameter or if its size is between 2.36 and 63 millimeters. So it is slightly different from what we have seen before. That's a different organization. We'll call a particle a sand if it is within the size of 0.075 millimeter, and 2.36 millimeter, and we can sub-classify it as fine, medium, or coarse depending on its size as well. Anything smaller than that, that is 0.75 millimeter, we also call it 75 micron. We call it silt or clay. Now, let's have a look at the letters we use to define the names. Some of the common letters we'll be discussing here. So letter G, you can see in this table, it stands for gravel. So if a soil has, say, 60 or 70 or maybe 80% or 90 even percentage of particles within the gravel size range, we call it a gravel. Basically, it's named by its dominant particle fraction. If a soil has 95% sand size particles or 60% sand size particle, we'll call it a sand. If it's a silt size particle dominating, we call it silt, and we use the symbol M for silt, and clay, C for clay. So that's the first letter in the name, depending on its dominant particle fraction. The second letter in the name of the soil, you can see they're listed here, PWHIRL. They indicate or they represent its behavior type. For sandy or gravelly soil, that is coarse grained soil, we use a P or W as the second letter. P stands for poorly graded and W stands for well graded. What these basically means, we'll talk about that in a second. For fine grained soil, we have mentioned before, it is often dominated by its plasticity. Then HIRL goes next to letter M or C and indicates if it's a high plasticity soil or intermediate plasticity soil or low plasticity soil, as the plasticity indicates or dictates the behavior of those soil types. Now let's have a closer look at the coarse grained soil, why we call some soil P or why we call some soil W, that is well or poorly graded. If we look at the first row of particles, we can see all the particles are basically same size. That means if we try to compact them, they won't be able to form a very compact mass. And you can refer to video 1 where we discussed an issue similar to this. If we have a set of particles which looks like this, we can see there are different size particles and a reasonable variation in size as well. So what will happen? This will be able to form a much denser or compact mass. Now, what if a soil forms a denser or compact mass? It has much higher number of particle contact. On top of that, it also has less degree of freedom for the particles to move. That means it will behave as a stronger soil. The third group of particles we can see here, you can see we have these big particles and then lots of small particles, some intermediate size are missing. So it's again will not be able to form a very dense or compact mass, at least not as good as these well-graded particles. So these ones, we also call it a poorly graded soil particles. Now, how do we know if a soil is W or P? To do that, we take help of this diagram. We call it grain size distribution plot. Now, this might at the first glance look a bit complicated. This is not for one soil. I have put 4 different soils. Now, what we are looking at in this diagram, we have plotted the grain size against something what we call percentage finer. Now, to understand percentage finer, we have to go back to how we got these data. So basically, this is a set of sieve, and these data are from an analysis done using this sieve. It's very simple, straightforward. What we have done, we have set up these set of sieve, and they have the aperture, sieve aperture. As we go down, the aperture reduces. So the biggest aperture will be at the top, and the smallest aperture will be at the bottom. So during the test, what we do, we take the known quantity of soil and throw it on the top and shake it for 15-20 minutes. And then what will happen? The soil will segregate, or these sieves will retain different quantities of soil of different particle size. Then what we have to do, we have to weigh them, and then that will tell us what is percentage finer. To give you an example, what is percentage finer? Just to make it a bit easier to understand, let's say we threw 1 kilogram of soil sample on top. This sieve retained 100 gram, and this one, the second one, retained 100 gram. Let me just write it in here. Let's say this retained 100 gram, and this one retained 100 gram, and let's say this one retained 50 gram. Now, percentage finer basically indicates the percentage of particle that has passed through that sieve. Let's say this is a 2.36 millimeter sieve, just an example, and we put 1 kilogram of soil, and this retained 100 grams. So how much has passed through? 900 grams. So what will be the percentage finer in this case? 90%. Now, for the second sieve, this has retained 100 grams. Now, how much soil has passed through? This has already retained 100 grams, and this has retained 100 grams. So the percentage of soil that has passed through that sieve is only 800 grams. So that is 80%. And if I do the calculation for this one, it will be 75%. Hope it makes sense. Now, once we have done that, we plot the sieve size as grain diameter, and on y-axis we plot the percentage finer calculated. And then we look at the shape of this graph. Now, how do we understand what these graphs mean? Let's start with this one. I'll put a cross in here, say this one. See if you can see in here, the soil sizes are within a very small range of sizes. There is a very steep drop in percentage finers. That basically means all the soil particles are within 0.2 to, let's say, 2 millimeter diameter. What that indicates, it's uniform soil. Most of the soil particles are very similar size, so it is a poorly graded soil. Now, in comparison, if I look at this diagram, you'll see it's reasonably flat, a sort of S-shaped curve, and you can see the particles are distributing over a much larger range. The biggest particle size in here is 20 mil, and the smallest is close to silt size particles, I think clay size particles, 0.002 millimeter. So it has a wide range of particle sizes and distributed over a large range. So this is what a particle size distribution curve for a well-graded soil look like. Don't worry about the other two. These two are the most common one. You might have to differentiate time to time. Just put some labels on the diagram. Gap graded, basically it's the name suggests. You can see in here the curve has become a bit flat. That means some particles within that size is missing. So that is basically a gap graded soil, and it is the third example in the previous slide. It is also a poorly graded soil. Anyway, moving on. So these are some example names, what a name for a granular soil or sandy soil or coarse grained soil might look like. So if we have a gravel, the first letter will be obviously G, and it can be either W or P, the second letter. So a gravel, we might name it as GW or GP, and same goes for sand. It can be SW or SP depending on its particle size distribution. If we have lots of fine particles in it, sometimes we use a secondary classification because these fine particles start dominating the behavior. So if we have more than 12%, we decided that will be a threshold value. If we have more than 12% silt, we call it GM. So in that case, the particle size distribution doesn't affect or control the behavior as much as the fine particles and the plasticity related to it. Now, when classifying a fine-grained soil, the particle size distribution doesn't matter as much. Why is that? Because the behavior of the soil is not very well correlated with the particle size and its distribution. Rather, it is better correlated with the term what we call plasticity, or how plastic they are. Plasticity is just a word that indicates how attracted the soil is towards the water, that is affinity of the soil towards water. And we often use these three terms, liquid limit, plastic limit, and shrinkage limit, to define the affinity of a soil towards water. Just let me explain. Now let's say in the first picture we can see lots of dry soil. So a clay soil will look like this when it is in a dryish state. Now if we add water to it, we can mold it to any shape. And then if we add more water to it, it will start behaving like a liquid. See how the soil is transforming from a solid state to a semi-solid state to a liquid state? These things are related to these numbers. Especially liquid limit is the water content at which the soil starts behaving like a liquid. Plastic limit is the water content at which the soil starts behaving like a semi-solid plastic, and shrinkage limit, the soil is very hard. Anyway, if you want to know about these limits in water content, they are also known as Atterberg limit. You can click on this video link and watch it. Now there is another quantity we often use. It's called plasticity index. We use it for classifying fine-grained soil as well. It's nothing but the difference in water content between liquid limit and plastic limit. And it's a very good indication how plastic a soil is. If we have a very high liquid limit and high plasticity index, it can be an indication that the soil is very high plastic. And if we have a plasticity index very close to 0, it's non-plastic fines. Sorry, it's a soil that is non-plastic, so its behavior is going to be dominated by its particle size distribution, basically. Now, to do this classification in the lab, we do some testing. Again, we call it Atterberg limit test. You will be able to learn about these testing apparatus in the video in a bit more details. I'm not going to discuss this anymore. And for your practical, I have created another video that will guide you through step-by-step process how we can classify a soil, but again, not using this sophisticated instrument, by feeling or touching, doing some very crude tests with it. You can come up with a classification as well. We call it visual tactile test. Visual means seeing and tactile means touching, and the engineer will often do it when he's in the field doing some preliminary investigation or data collection. So watch for that video, and that will be also a part of your assessment task 1 as well. Now, there are some examples of what fine-grained soil or clay or silty soil name might look like depending on its plasticity. It might be Cl, Ci, or Ch. Ch is very high plasticity. On the other hand, Cl is low plastic soil, and higher the plasticity, more difficult it is to deal with. That's basically to do with it's higher the plasticity, the change in volume is higher. We'll talk about that a bit more in a later lecture. For this lecture, that's it for today. Here is some image notes. The images are sourced from these sources, and in the next video we'll be starting to talk about soil behavior. See you then. Thank you.